Okay, so welcome again, and let us continue from where we have left. So, in last class, we have introduced the concept of the Cauchy's theorem, which relates the traction vector to the Cauchy stress, and the benefit was that we know the directions and the components of the Cauchy stress. So Cauchy stress is only having 9 components, whereas the traction vector can have infinite number of directions in infinite number of surface elements. Okay, so that is why it was beneficial to cast the traction vector in terms of the Cauchy stress, because the directions or the numbers are limited. Okay, so now uh, so the basic or the formal definition of traction force is given by this thing, that is traction force is the force per unit surface area. But uh, the definition is traction force is given by this thing, that is limit del A tends to del A star del A by del A. So the question arises that why del A tends to 0 is not right. So that is because the concept of continuum. Okay, now if you say that we are taking a very small area, then in that small area the magnitude of force can vary significantly, and giving a time variant stress or a time variant traction vector. The same concept applies for the density also. Okay, if you are taking volume tends to 0, so for density, if you are taking that rho is equal to limit del v tends to 0 del m by del v, then it is not valid, because in this situation if you take so if you are taking the volume to be very less, then the concept of continuum is no more valid. Then you have to go for either molecular dynamics, okay, or any other thing like kinetic theory of gases, etc. Okay, so uh, to valid to make valid our continuum hypothesis, we have to choose such an area or such a volume beyond which the or above which the continuum hypothesis is valid. So that is why this del A star is okay. Now um, following the basic definition of traction vector, the surface force becomes, okay, the surface force becomes what? So if I take this kind of a body, and so this is a body or the control volume, and in this control volume I have this control surface. Okay, so this is dA, right? Now in this control surface I am having a traction vector maybe in this direction, so this is given by theta ti eta. So you should always remember the convention that the indices are applied as the subscript and not as a superscript. Okay, so eta is the what I'm writing here again, that eta is the unit normal. Okay, unit normal of dA. Then force on dA, that will be what? T I eta. So and what is the direction of the force? That is nothing but I. So this I is denoting the direction or component of the force. So if you are considering the Cartesian coordinate, then I can be 1 2 3, that is x y z, right? So this is a vector. I have already introduced you with the indices notations, okay, and how it is applied. So by this time I think this should be okay, that y t I eta is a vector. Okay, so so this is the force on the surface dA, right? So total force, total surface force on CV, on the control volume, so this will be integration dA over which, not on the control volume because it is a surface force, it is acting only on the surface. Okay, so over the control surface, right? So this will be the force. Now work done, but we are not interested on the force. In case of deriving the energy equation, we are interested in finding the work done. So work done per unit time, right? That is the rate of work done on dA. That will be what? So this is the force. So power means force into velocity, that is the work done per unit time, right? So this velocity will be in the same direction of the application of force. So I am taking uy. So this TIUI is nothing but the concept of uh, the the dot product. So this is a vector theta dot u, velocity, right? And we know that the power is given by F dot V. So Ti eta uy. Okay, so this will be the work done. And similarly, total work done, WD I am writing, by surface force is equal to Ti eta uy dA. Clear? Okay, so this will be CS on CS. Okay, so this is our surface force. Now what will be the body force? So body force is pretty straightforward. So this body force, okay, body force will be, let us take Bi as the body force vector. Okay, body force vector per unit volume. Okay, per unit volume. So this is the body force vector per unit volume. Then total body force, uh, you integrate BF all over the volume. Okay, then it becomes the total BF, right? Okay, so now all the components in terms of their mathematical descriptions are available. Okay, so now let us write the thermal energy equation. So sorry, so this is not the thermal energy equation, this is the total energy equation. So first let us write the LHS. And what is the, so this all terms, heat transfer, heat generation, work transfer, all terms comprises to LHS. Okay, so now let us write LHS. Okay, LHS of total energy equation, LHS of total energy equation, right? So that will be, so first the heat flux term, and that is given by what, this thing, right? So let me write this, minus q prime, okay, dot nda. Okay, q prime dot nda, and I can write this as q prime j cap, and eta, n is the unit normal, I am writing that by eta. Okay, dA. So by this time I think you are conversant that this q double prime j into eta j is nothing but the dot product of q and eta. Okay, so this thing integral over the control surface, right? Okay, next term is heat generation, and and you should also remember the significance of the minus sign in the heat flux. So heat generation is the direct term. So this thing, where q triple prime is the heat generation rate per unit volume. Now comes the work done rates, right? So first is the body force. Okay, so body force work done will be in the similar manner, Bi eta I dV. Okay, so mind it, this was the total body force. Similarly, the total work done by the body force is the Bi/Uy dV, integral over Cv, because Bi/Uy is the work done on that particular volume element. That is, if you consider this kind of a body, and let us say that this is a dv. Okay, so for this dv, the work done by the body force is BI-UY. Okay, okay, now let us continue the surface force. So that will be Ti eta Uy dA Cs. So this is the energy equation. Now let us do some modification to the energy equation. Okay, so what sort of modification is will be this? Let us see. So this term, now we have to convert all the area integrals to the volume integrals. Why? You will be see in a moment. Okay, so and which tool, which calculus tool is useful to do the same? So that is the Gauss divergence theorem. So Gauss divergence theorem says that if you have either any vector or scalar, so for a vector, let us say A is a vector, so A dot eta cap dA, so that will be divergence of over any surface area, any closed surface area, okay, any closed surfaces, so that will be divergence of A dV. So this volume will be the volume bounded by the surface S. Similarly, this will be also this so this was what, q dot nda. Then in the vector notation, this will be this dv over cv. Now in the indices notation, divergence will be what? Now divergence will be, let us see that if I have a vector a, so a is having components a1, right, a1 e1 cap, a2 e2 cap plus a3 e3 cap. Now e1 e2 e3, you would take this analogous to x, y and z, and our nabla operator is, okay, I cap or e1 cap del x1 plus e2 cap del x2 plus e3 cap del x3. So essentially this becomes what, del a1 as, okay, I am writing this summation I runs from 1 to 3. I think this is clear. Now in Einstein's indices notation, this is nothing but this, and also you can write any indices instead of I, so I am writing here j, right? So similarly this can be written as minus of del qyj by del xj dv. Okay, so this is in terms of a volume integral. Okay, now this term will is already in a volume integration term, so this will remain, and this term is also, again, we don't have any problem with this, so this will again remain. But this term now, by Cauchy's theorem, I can write this Ti eta as sigma, what, as sigma ji, right, or ij, sigma ji eta j then uy dA, right? Let us confirm once that was it sigma ij or ji? It was sigma ji. Okay, so till now I haven't said that sigma ij equal to sigma ji or not. Okay, I have not applied any assumptions or anything, so don't write it as sigma ji or ij. Sigma ji is not equal to sigma ij up till now. Okay, so and this is over cs. Now these all things are scalars and not vectors. This is this and this. Whenever you write the indices notations, so those indicate a vector. Sigma ji is indicating a tensor, but sigma ji is a scalar. Sigma ji is a component of the tensor sigma. So ui is indicating a vector, but it is essentially a scalar. Okay, so these all are scalars. Now, if these are scalars, then I can first multiply sigma ij with ui. Then I can do the multiplication of eta j with with this thing. Now just take a look on this. This sigma ji into ui, how many free indices this is having? So free indices it is having one, that is only j, I is repeated. So that directly means this must be a vector. So this is a vector, and this is having the free index j, and this is also a vector. So this vector, if it is termed as a, this is having a free index j, it is multiplied with some eta j, then it is a dot product, and this whole term is as good as a dot eta dA. Then this whole term boils down to divergence of a into dv. So divergence of a into dv means daj into dxj, right, into dv. So this over the cv, and now a is what? A is sigma ji ui. So this whole term boils down to this whole over cv. Okay, so now the LHS is ready in terms of a volume integral, right? Now let us modify the RHS. So okay, now RHS, sorry, okay, so now let us come to the RHS. So this is RHS of energy equation, right? Okay, so RHS of energy equation, this is this term, right? So I am writing it again from the scratch. Okay, so RHS of energy equation is equal to what? It was del T of rho E dV and plus over CV, and this is over CS rho E V dot eta dA. Okay, so this A is the total energy per unit mass. Okay, so again we have to cast all the terms in terms of their volume integrals. So this term will remain same, and this term again let us write it in terms of index notations. So rho is a scalar, is it is not a vector, and energy rate is also a scalar, it is not a vector. And then we have v, so v is a vector, so let us take this thing as vi. Okay, so and it is dotted with eta I, so into eta I because it is a dot product dA. So similarly, because it, so they, so this rho is like a number, so I can take into the divergence. So this will be this actually in vector notations, and but I am doing this in a indices notation, so this will be this. And don't be confused with why this, so this was I, now I am writing j. uh, why I can write it like this? Because I and j both were repeated index, and the repeated index I can write as any alphabet. Okay, so this will be the RHS of energy equation. Now let us do LHS equal to RHS. So LHS equal to RHS, right? Okay, so LHS equal to RHS will give us what? Okay, so I will write RHS equal to LHS, both are same. Okay, so now but still I am writing the actual thing, it is RHS equal to LHS, RHS equal to LHS. Okay, now the RHS is becoming the LHS just for the equation to look good. Okay, So I am taking all the volume integrals under the same integral sign. So this is del t of rho e plus del of rho e vj del xj whole of dv. Now, one more thing. Have you noticed that I am writing this thing directly as del rho e del t dv? So can I write this so easily? I can only write this having an assumption that the CV is non-deformable. Okay, that is the volume is not a function of time. Okay, so CV is non-deformable, and if the CV is deformable, then also the equation can be modified. Okay, using the Leibniz rule. Okay, so now this is our one side, and the other side is again all under the same integration sign. So this was minus del qj del xj, right, plus what, q triple dash plus biuy plus del sigma ji uy del xj. Okay, so this will dv. Just let me see that have I written the all the terms correctly. I have included this and this thing. Okay, okay. Now can I write this whole term equal to this whole term? So a question mark arises. Can I write this? I can write this only because dv is arbitrary. Okay, because this is arbitrary. Okay, and that is why these two terms must be equal for each and every dv. So had I chosen dv having a bias in my mind that dv should possess this criteria or that criteria, then I don't have the right to equate these two terms. So equating these two terms, what they will give, rho del e rho t. So rho, I mean del rho e by del t by del rho e vj del xj, that is equal to minus del qj double dash del xj plus q triple prime biuy plus del this thing del xj. Okay, so this is the total energy equation. Okay, so this is the total energy equation. What, this is what the total energy equation. Okay, total energy equation, correct? Okay, so now let us focus on firstly the LHS side. So this term, let us apply the rule of differentiation on the multiplication. So in the first term, rho del e del t plus e into del rho del t. For the second term, let us take the rho, uh, so del rho e. Okay, so let us maintain the order of the terms. Vj. Okay, so I am right. I have written here um, this uy as my velocity. So maintaining the uh, same signs, I should write here uj, not v. Okay, so now uj, sorry, uj del rho e del xj plus rho e into del uj del xj. Okay, so will it give the correct thing? Just let me see that. If I take row common, no, I can cast it in terms of things also. You will see that how that why I have removed that thing. I mean, although that was correct, I can write is I can write this in terms of rho into del e into this, right? And what else? Plus, uh, so is this correct? Okay, so let us do. Let us first do, not having any prejudice in mind. Okay, so we can write this equation, this LHS term, in this format, right? Okay, so now if I can take this E common, okay, this E common, okay, no, the previous thing was right. I apologize for this. I really apologize for this. Actually, I don't have these things uh, practiced before the recordings of video. I have to do it from the scratch. So sorry for making these mistakes. Extremely sorry. So ui, so u ji common and del rho e del xj plus, okay, plus rho e del ui del xj. Okay, so e should be there out. So, and what my objective is to separate the continuity equation. So e should be out. Okay, plus rho uj and del rho e del e del xj. Now I think this should be okay. Okay, so I am deriving all the things from scratch, okay, by myself. So that is why I am making such silly mistakes. So just forgive me. I hope you will do. And I am extremely sorry for these things. Okay, so now I am taking common from these two terms e, okay, and from these two terms rho. So it will become rho into del e by del t plus uj plus uj rho e del xj plus from these two terms e taking common, so this plus this thing. Okay, now this is 0 by continuity, right? Continuity, and this becomes what? Rho into this. So my objective was only to come into this expression. Okay, otherwise there was no other significance of this mathematical jugglery. So then the equation becomes what? This thing, that is uh, rho into this thing, right, equal to, so our minus, sorry, this this j del xj. Okay, so let us write in terms of the vector notation, then we will be acquainted with the vector notation also. So this is what? Divergence or the grad of q. Okay, divergence of q. And this is, so this is not a vector, and this is what, B dot U, and this is divergence of sigma into U, right? So minus of divergence of this plus this thing plus B dot U, okay, and plus divergence of sigma. Okay, so I am writing an upward arrow, I mean a rightward arrow in the top of the letter to denoting it as a vector. So let us give uh, two slashes or two horizontal slashes below the letter sigma, sigma, to indicate it as a tensor into U, right? So this, so this is the what, vector notation of the energy equation. Okay, now let us take this term. This is very important term. Okay, the rate of work done term by the surface forces. So del xj sigma ji uy. Now you will see that why the indices notations are so useful. It actually the indices notation seems to be very threatening, that working with it will be very difficult and will be very complex, but actually it simplifies the things a lot. So this will be what, sigma ji del uy del xj plus uy uh, sigma this thing, right? Okay, so now these two surface forces, if I have to um, okay, so this is, now what do these terms indicate or mean? Okay, so any force, if it is applied onto a body, it can increase its kinetic energy, its potential energy, or maybe any internal energy. Okay, so potential energy is clubbed here into the internal energy term, or actually the macroscopic potential energy, that is clubbed into which term, can you say? So potential energy can be because of any opposing force, like gravity, like a spring force. Okay, so work done against that kind of force would lead in into the conversion into the potential energy. So here the body force term B dot U, if I say that the body or the control volume is in the uniform gravitational field, then this B is G, and then this B dot U will be the rate of change of potential energy. Okay, so now these two forces, one of these two force will lead to the change of mechanical energy or the kinetic energy, because the potential energy has been taken care of, and the other one will be any other thing. Okay, the maybe the change of internal energy. So we have to find that which term is causing the change in uh, which energy. Let us do that. So for that, let us write the mechanical energy equation. So if this term uh, if this term will occur in the mechanical energy equation, then we can say that this term is responsible for the change of mechanical energy and not in the change of internal energy. And if the vice versa occurs, then the vice versa decision will be taken. So now the mechanical energy equation. Okay, so mechanical energy equation. Okay, sorry. Okay, mechanical energy equation. So we know, okay, so first let us start from the very basics. Applying RTT on n equal to interpretation of VDM, that is linear momentum. So small n will be velocity. Okay, so this will give us what, del of VDM, okay, del T respect to system, right? That will be equal to del T of rho V dV with respect to CV plus this will be CS, this will be rho V and V dot eta. Actually this is V relative, but we are taking that there is no relative velocity. I mean the velocity of the control surface and the flux. Okay, I mean the control surface is fixed actually with respect to the flux going out. So this thing, right? And now again this thing will be F external, summation of F external, and F external will be because of again BF and SF. I hope that you know that what is BF and what is SF, right? So I am giving you the missing links so that amidst or in between the lecture you you get the time or you get the opportunity to recap the things by yourself. Now the BF I am writing directly here. Okay, so this will be BI dV, right? And this is um, what, traction against sigma ji. Okay, so this will be xj dv. Now your task is how these things come. Okay, I am not doing the whole derivation, but your task is to find that how this thing can come. This uh, del sigma ji del xj. Okay, then this will be an exercise over the indices notation for you, and this will be what, and this is del rho v, or in indices notation let us write directly del rho v, not v actually, I am doing the same mistake, u, let us write u because I have written u previously. So u ui del t, okay, dv, and this is what, okay, now this term I will elaborate. Okay, so first concentrate on this term. This is a dot product, that means this whole term, that is v dot eta, this is essentially a scalar. So this scalar can be written as uj with eta j. Okay, and this is the vector and this is the same vector, these two. So I cap, uy cap. So let us say that I am writing the equation for the x coordinate or I equal to 1. So this I must be the only free index in every term of the equation. So in this term also I have only this I as a free index, this I as a free index, right? So in every term of the RHS also I must have this I as a free index. So here I as a free index and here j as a repeated index and I as a free index. And rho is there, so this term in total will be rho ui uj eta j dA, right? Integral over the control surface. Okay. Now I have something different, right? So this will be uh, okay. Now this is the same kind of the term, that is rho v into v dot eta dA. Okay, so rho v into v dot eta dA, and here it is rho uy uj eta j dA. So if I have to write the divergence, then this will be this rho v dv. But if I have to write the indices notation, okay, then what will be this? Will it be del of rho ui uj by del xi or del xj? Okay, so just let us have a look here, that is in these terms. Okay, so here I was having, okay, so here I was having qj eta j dA. So I was having eta j dA, that is why I was having del xj, and here also I was having eta j dA, that means this total thing is dotted with eta. So this the free index of this total thing will be the same as the free index of eta, because if I am drawing a dot b, then the free index of a must be the free index of b. Okay, and the divergence will be having the index notation will uh, with this del x j or del x ak del x k. So this xk have to be the free index of ak. Okay, and that will be the free index of eta j. So in essence what I am trying to say is this eta j, this j, that is the subscript of eta, will denote the free index of this vector. Okay, or it will denote the free index with respect to which the derivative in divergence has to be taken. Okay, so now, and that is why here I have eta j, then I have to write here x dv. So this is cv, right? Okay, so now writing the whole equation, I have what del, okay, um, del rho uy del t plus del uy uj del xj equal to vi plus, and for the same reason, because dv is arbitrary, I can drop the term dv and equate the both sides. Okay, now it is your task to show that this boils down to this. Okay, in the similar manner, bi plus this thing. Okay, now this is a force balance equation essentially, the rate of change of momentum, that is force. Okay, so if this is a force balance equation, then to convert it into a rate of change of energy equation, I have to multiply it by velocity or getting a dot product with the velocity. So this force balance equation is having I as a free index in each and every term, and this free index means the direction of a vector. So to get the dot product, I have to multiply with the same indices and the velocity vector. So this will ensure. So this is to convert into uh, energy equation. Okay, energy equation, and precisely mechanical energy equation. Okay, so multiply with u, so di dt into u and biuy plus, so this is this. Okay, Now this I can write as capital D dt of half uy square, okay, and this is equal to this. So this is the mechanical energy equation, okay, this is the mechanical energy equation. Now see that both this term and this term was there in the total energy equation. So out of that total energy equation, so now let us analyze, okay. So here, so this LHS was denoting, so this LHS was denoting the rate of change of total energy. So all these terms, this heat flux, this heat generation, this work done by body force and work done by surface force, all these terms or all these things were giving rise to the or giving a diminution to the total energy. Out of this term and one part of this term is only contributing towards the mechanical energy and not towards the internal energy. And so this is the actually macroscopic potential energy, and this term, okay, and this term is having the internal energy, okay. So okay, I mean sorry, this term is increasing the kinetic energy, that is this thing. So actually, and now you can also do it like this. So let us let me give you some analogy. So for gravitational field, so an example, so for an uniform gravitational field, B is what? B is mg, okay, per unit volume, okay. So that will be rho g, right? It will be bi, so this will be rho g u ui, okay. This bi ui times, so this is bi ui, right? And that is essentially I am, so g is not changing with time, so that will be rho g u, okay. So let us write it as del, because you can change with position also, this del del t, rho g into u, right? So this is the potential energy, sorry, x, this will be x. So rho gx is what? Potential energy per unit volume, okay. So this is potential energy per unit volume, or I can write g as the uh, gradient of, okay, gradient of gx, right? Or maybe gz actually. So because the vertical height we generally represented this as this, okay. So and if g is acting towards the downwards and I am taking the z towards upwards, then this will be as minus g, okay. I am just giving it as an example. So this total term can be written as, okay, uh, minus g into gradient of g into uh, okay, u maybe, or gz and whole over del del t, okay. And now this thing can be written as minus d dt of gradient of gz. And why? Because if you write the total expression, that is this term is nothing but this thing plus u uj del of gz by del xj. So I am taking that this g and z, I mean both are not the function of xj. This g, at least the, sorry, the gradient of gz is g. So this g is not a function of x. So this term is 0. So essentially, if now I can take this total term into this LHS, and that will be okay. So this rho will be there. Okay, so I mean this all things will be into a row. So this row was there. So rho into d dt of half q square plus some pi. Okay, so this pi is nothing but gradient of gz or gradient of the potential. Okay, okay, so now this is the now this is essentially the total mechanical energy, that is the macroscopic kinetic energy and macroscopic potential energy. So why I have done this thing, I have shown you this example, because you can be confused. That is, I am saying that total mechanical energy, but potential energy should come under the mechanical energy, right? Because it can be converted into mechanical energy right away, right? I can store some water in a reservoir and I can convert it into the kinetic energy. So mechanical energy is a very good source, handy source, and for mechanical work done, to do mechanical work done. So this the total energy equation as well as this mechanical energy equation is having both the kinetic and potential energy term. And you can see that if this increase, this has to decrease. I mean, uh, in so apparently these are having the same time, same signs. Okay, but if this is a potential, if this is the potential energy, then if the potential energy decreases, then the kinetic energy has to increase to maintain the energy balance. If the total I mean if the body is in a conservative force field, okay, or conservative energy field. So okay, now this is the mechanical energy equation. Now our task is, so our objective is, for convection we are interested in the temperature, and temperature comes from the internal energy. So how can we get the internal energy equation? So internal energy is equal to total energy minus mechanical energy. So total energy equation minus mechanical energy equation. So now our objective is to find the internal energy equation. Okay, so internal energy equation, and that is total energy equation minus mechanical energy equation. So let us write it directly. Okay, so this is rho d dt of, that was E, minus half ui square. Okay, and this will be what? In the RHS of total energy equation, I had this and this term common, so these terms will be cancelled out, and other terms were qij, this thing plus this thing, right? And what? Now plus this term was not there, then the counterpart of this, that is sigma ij del uy del xj. Okay, so this is the internal energy equation, right? And because, okay, so now let me write the final form. Di dt is equal to minus plus q triple prime sigma ji del uy del xj. Okay, this I is E minus, okay, kinetic energy, internal energy. This is okay. So this is the internal energy equation. Internal energy equation. Okay. Now we are not happy with this, because in convection our end objective is to find the governing equation for the temperature. Okay, find the governing equation for the temperature. So first let us find something in terms of the enthalpy. So I is internal energy. Now our objective is to find dHdt, the governing equation for enthalpy. Okay, so this is the objective. Now H is what? H is I plus uh, P by rho, right? That means I equal to H minus P by rho. Okay. Now I have showed that this is equal to what? Del of rho I del T plus Ui or Uj del of rho um, rho okay, small I no, not small I, this thing um, okay, am I writing there? Okay, yes, this will be Ui and this is del xj, right? So let us visit once more. Have I written the right thing or not? No. This will be this only. This will be j. Okay, so let us actually visit. I have done the total derivation. Okay, this thing I have written as rho into capital dE by dt. So in terms E, so instead of E, just put I. Okay, so from this term now I am going to this term. So this is rho, I mean del t of rho E by del xj of rho E uj. Okay, so this is this term. Now it is correct. Okay, so now that means rho I equal to rho h minus p, right? So just put it into this. So that would give us uh, rho h, okay, so minus del p del t, okay, and then plus, so rho I means, so rho h uj del xj and minus del what, minus p uj del xj, right? Okay, so this two term, this and this will be uh, rho into dHdt. So now this jugglery between this form, okay, between this form and this form, this should be in your mind. Okay, this jugglery between these two form, this should be in your mind. Okay, so if now, and these two terms, what they will give, so minus I am taking common, so del p del t plus, so uj del p del xj plus p into this, right? So this is equal to, so this is equal to rho into dHdt minus, so this is this, right? And this is the same, so this minus this plus, okay, now this is what, this is actually divergence of u vector or v vector, right? Because del uj by del xj is equal to del u1 by del x1 plus del u2 by del x2 plus del u3 by del x3, and that is divergence of vector u. Okay, so in terms of enthalpy, now I have the equation. Okay, so let us write the equation in terms of enthalpy again. So this will be what, okay, so rho into dHdt is equal to dp dt minus p into this right? Okay, so plus q triple dot minus this, right? And plus what else was there? This thing, sigma ji del of uij del xj, right? Okay, so I have now this thing. This is in terms of enthalpy. Okay, so now the time has come to cast it in terms of a known fluid or known solid. So this thing was valid for almost any substance. Okay. Yes, for solids this u could be the your this u should be your displacement. Okay, and for fluids this u should be your velocity. Only this difference will be there for solids and fluids, but all other things should be there. Okay, and also for solids generally we don't have the term enthalpy, so for solid this internal energy equation is enough. Okay, so this equation is actually relevant for the fluids because this equation has been cast in terms of enthalpy, and enthalpy is generally is containing a flow work and solids do not flow. Okay, now okay, so now our objective is to cast it in terms of a known fluid. So which fluid is the most simpler most I mean which fluid is the simplest fluid for the engineering application? The air and water, right? So if I consider water, then let us consider a fluid that is okay. Now consider incompressible, okay, Newtonian, Stokesian. Okay, so these two terms, I mean, let us not have this term incompressible by now. Okay, let us consider this Newtonian, Stokesian. Okay, let us consider Newtonian, Stokesian. Okay, homogeneous isotropic fluid. Okay, homogeneous isotropic fluid, right? So if I am having this, okay, and obviously maintaining, okay, that is embedded in the Newtonian assumption, I will tell you. Now our objective is to correlate this with the velocities, I mean this ui. Okay, why? Because you will see in Navier-Stokes equations also, if you don't do this, then you have much more components than the number of equations. But if you cast this sigma ji in terms of ui, then your all the unknowns of sigma ji will boil down to the, I mean will boil down in terms of ui. So your number of unknowns will decrease. Okay, so how can we do that? First of all, this thing, okay, this is the velocity gradient tensor. So this can be this, I mean this can be written as this plus this. Okay, that is this minus this. So this is essentially the rotation, or okay, so this is essentially the angular velocity. Okay, so this is the rotation term, and this is the deformation term. Deformation term. Okay, so if I equal to j, then linear deformation. If I not equal to j, then angular deformation. Okay. Now, then this sigma ij has nothing to do with rotating the element. This is only what? This is only deforming the element. Okay, um, and we are concerned here about the deformation, right? So this is termed as, okay, EKL or EIJ. Okay, so this is termed as EIJ. This is termed as EIJ because it has two free indices. Now don't be confused that I have I here and I here, so this is a repeated index. Just always remember, this is a term and this is a term. So in this one term I have I as a free index, also j as a free index. So each term is having two free indices. Then this whole term must be a second order tensor. Okay. So now Newtonian means, okay, Newtonian means what? Newtonian means this will have a linear relation. Okay, linear relation. So Newtonian assumption simplifies the relation between this and EIJ. So linear relation. Okay. In our world, everything is non-Newtonian. Okay, nothing is linear. Okay. In engineering things also, I mean, not nothing is linear. We can have almost accurate result in case of water, considering it as a Newtonian fluid. But we know that for persons we don't have the Newtonian assumption. Everything is very complex, right? We don't have a linear relationship for us. So uh, now, so let us have something like Cijkl into EKL. So how can I write this equation? So this is like sigma equal to C into E. So this is a linear relation, but as both sigma and E are tensor, I cannot write C as a constant or a scalar. Okay, so EKL, just see, EKL is a second order tensor. So I have to multiply by something to make EKL, I mean to convert EKL into another second order tensor. So here I have two free indices, and here I have, and here also I have to have two free indices. Okay. Then to do that, if I was having here one indices, let us say Ci. So one option is I is not common and I is common. So if I is not common, so then I have here three different free indices. So then this will be not a second order tensor. And if I is common, then Ck into EKL, so here only one free index, then it is also a not second order tensor but a vector. Now if I have two free indices, so if the two free indices are not common with KL, then this is a fourth order tensor because it is having four free indices. And if one of them is common, so CIKEKL, then also it is a, now I can write this K. So this K is a repeated index, this I is a free index, and L is a free index. Then I can write it as a uh, then I can write it as a second order tensor. So one option could be this. Okay, one option could be this. Another option could be Ki equal. Okay, but these options will not work because we also have to maintain the dimensions. Okay, and the other option is, so why that option will not work? Because I have to have two different free indices. Okay, because I have to have two different free indices here from that EKL. Okay, because if I am having here also k, then this will be directly related to this ek. Okay, so no transformation is there. I mean, this component is directly related to this component, but I have to give a formula to give an independent transformation. Okay, so this ijkl, so this k and l are repeated, so this will be cancelled out, summed over, and this ij are free indices. Okay, okay, so now I have the assumptions of isotropic and homogeneous. So homogeneous means direction independence, and isotropic means what? Isotropic means if I have four vectors like A, B, C. If I have these three vectors, then these are having some angles like theta or maybe something like gamma. Isotropic means if I do some change in coordinate system, okay, coordinate system, so then the whole thing might be rotated like this, CBA, but this will be theta and this will remain as gamma. So the I mean the relative angles between two vectors will remain same, and the relative angles, so that means A dot B uh, will remain same. Similarly, A dot C remains same and B dot C, because this dot product gives us the angles. Okay, all the sign product can also give us the angles still. Okay, okay. Now to findCijkl, there is a long proof in tensor algebra that if this thing hold andCijkl is uh, ifCijkl is isotropic, then I can write asCijkl as some alpha into delta ij delta kl plus some beta into delta ik delta jl plus some gamma into delta il delta jk. Okay, so this is the I mean the formal proof is very long. I will give you a very nice short proof, and I have learned this from an NPTEL lecture given by Professor Suman Chakraborty. Okay, so also you can refer to that if you have any doubt. Okay, so um, nowCijkl, this is a fourth order tensor. Okay, so fourth order tensor is having four free indices, and the vector is having one free index. So this can be, so let me write it in words. So this can be represented by mathematically, okay, I am not saying anything with a physical meaning, mathematically represented by four vectors. Okay, that is AI, BJ, CK, DL. Okay, so A is contributing for the free index I, B is contributing the free index J, C is contributing the free index K, and D is contributing the free index L. Okay, now if I have to define a scalar or convert theCijkl to a scalar S, then I can do this thing, multiply with A, Bj, Ck, Dl. Now see that there is so there are no free indices, everything is repeated. Okay, now this scalar, now this is a scalar, so dot product also gives us some scalar. So now as it is isotropic, then I can represent this total scalar in terms of the dot products of A, B, C, D, and obviously different combinations of the dot products, because if you take only A with B and C with D, then the other angles will be not there, but you don't have that right to take that bias, right? So I can write this scalar in terms of some dot products between these four vectors, because I have told that this a b c d is representing the CIJKL. Okay, so that will be alpha into, so let us take first the combination of a b and c d. So every combination, if I take AC and BD, every combination, the angle between AC and BD will remain same in any coordinate system. Angle between AD and BC will remain same in any coordinate system. So I have to take all such combination. So AI, BI, then A with B, then C must go with, so CK, DK. Okay, so you could have write here ALBL. So because this is the repeated index notation, plus beta into, now A can go, now A can go with C. So AI, CI. I have removed the J, but you could have written AJ, CJ. So AI, CI and BJ, DJ, plus another constant gamma into AI, now DI, so BJ, CJ, CJ. Okay, so A can come with B, A can come with C, and A can come with D. Then all other combinations are ensured. Okay, no other combination can be there, because A can only come with B or C or D. Okay, so A is here with B, C is D, A is here C, B is with D, A is D, B with C. Okay, now alpha, beta and gamma are the constant of proportionality. Okay, so here this step is very important. The main reason is isotropic isotropic nature. Okay, and that is why angles between each vectors are conserved. Okay, okay, so now, okay, now let me introduce you with a very special second order tensor, that is delta ij. So delta ij is termed as Kronecker delta. Okay, and it has the property that delta ij is equal to 0 if I not equal to j, and it is 1 if I equal to j. And delta ij is symmetric, that is it is equal to delta ji. Okay, so now you can you tell me that if this is wrong or right? So aj is equal to ai delta ij. So in this equation, if I put I equal to j, then only delta, it will be jj, and this is 1. So this total thing is essentially aj. So if I have now am delta mq, so this will be aq, right? Because only if m is q, then delta mq is 1. Okay, so this will be, now I can write it as, so ai, so my objective is now taking ai bj ck dl common from these three expressions, because ai bi all are scalars. So okay, now I have bi, I have to convert it to bj, then it will be delta ij bj, it is essentially bi. I have ck, ck is not a problem, but dk is a problem, I have to convert it to dl, so delta kl dl, right? Okay, plus beta, ai is not a problem, ci is a problem, ck should be there, so that is why delta ik ck. Now bj is not a problem, sorry, not plus, it was into, now bj is not a problem, but dj is a problem, there should be dl, so delta jl dl. Okay, plus gamma into, ai is not a problem, di is a problem, so delta il dl. and again Bj is not a problem but Cj is a problem, so delta Jk Ck, right? So now if I take Ai Bj Ck dl common, then I have Ai Bj Ck dl common with what, alpha into delta ij delta kl plus delta ik delta jl, okay, plus okay, so there was a beta plus gamma into delta il delta jk, right? So this thing is equal to Cijkl into Aibjckdl. So this is equal to Cijkl into Aibj, okay, Aibjckdl. Then this will be, I can write Cijkl is equal to alpha into delta ij delta kl plus beta ik delta jl plus gamma il delta jk, okay. Okay, so I have proved this equation, okay. Okay, so let us stop today. Now if you have any doubt, please let me know. I'll be very glad to hear your doubts. And I always say that I am also a student. I will always be a student, learning each of these subjects up till my life. So, and if you find anything illogical or anything you find can be explained in a better way, you can also let me know. And you can also let me know if you have suggestion over the style of my explaining, okay. And up till then, take care, and you can share me um, your questions regarding gate or any exams, because I have appeared in TOEFL and GRE also, okay. My GRE marks was 319, not very good, and in TOEFL it was 101. It was also not very good, okay, but still, if you feel that I can help you, you can always contact me. I have some friends, those who have scored very well. I can give you their contacts also if you want. So any type of help I can do for you, then you can always ask me. I am there, okay. So until next time, take care and goodbye. So let us meet in the next video.